This question came in 2012 for 4 marks. It's a linked answer question or common data question. So the data is given here and there are two questions, question 1 and question 2, each carry 2 marks. So the question is, in the three-dimensional view of a silicon n-channel MOS transistor shown below. So a three-dimensional view of a n-channel MOS transistor is shown here, okay, where del is 20 nanometer. The del is this del, okay, this is nothing but this del. Del is 20 nanometers. The transistor is of width 1 micrometers. If you see here, this is actually the length of the channel. This is the width. So the width is given as 1 micrometers. So let's take width is 1 micrometers. The depletion width formed at every PN junction is 10 nanometers. The depletion width, so let's say depletion width for PN junction is 10 nanometers. Now where are these PN junctions? As this is told as n-channel MOS transistor, the substrate is P, so that when you apply potential beyond threshold voltage, it becomes N-type here at the surface, which is inverted. And these two regions, the drain and source, this is source, are N-type. Okay, so that when there is P and N, there will be depletion region around them. That's a depletion region width given as 10 nanometers. Now the relative permittivities of silicon and silicon dioxide are given. Okay, so epsilon R of silicon is 11.7 and epsilon R of oxide is 3.9. Now epsilon naught value is given here. Now let's see what the questions are. First one is the source body junction capacitance is approximately. Now what is source? This entire region, so in fact in 3 dimension the other side is not given here, so it is up to imagine. Okay, this is how the source will be. Source here is a 3-dimensional figure, right? So let's draw how it looks. So 3-dimensional point of view, the source would look something like this. Okay, so this is on the back side. This will be like a tub. Okay, so now this terminal is called source. Now if you observe, there is this substrate and substrate has a contact. If you see here, the question is source body junction. The body is nothing but the substrate contact, which is body. Source to body junction capacitance. Now if you observe here, which sides the junctions are present? If you see front side also, there will be one junction, back side one junction, right side one junction, left side one junction, and bottom side one junction, right? So we need to calculate the depletion capacitance here, okay, which is the junction capacitance for all the sides and add them together. So before we add them, if you see all the units are in micrometers, so the area will be in micrometer square. So the area most of the cases for this is in micrometer square. So before that, let me just mark the notations here. This distance is 1 micrometer and the depth is 0.2 micrometers and this width here is 0.2 micrometers as given. Now everywhere you will have area micrometer square. So instead of actually calculating capacitances for each side, let's find capacitance for this depletion region per micrometer square. Okay, let's find that first and then add all the areas and multiply so that we get the capacitance. Then we can choose the answer here. So for that, let's find the junction capacitance per unit area. That unit area we want it to be micrometer square. So let's find this. This is epsilon naught epsilon R of silicon, because we're talking about depletion region formed in silicon, divided by the depletion width. The depletion width is actually given 10 nanometers. So this is XD. which is given by epsilon naught is epsilon r is 11.7. I am flipping them, okay, times epsilon naught is 8.9 times 10 power minus 12 farad per meters divided by 10 nanometers. 10, I am going to write this in micrometers, so it becomes 10 power minus 3 micrometers. Now we want to find this value in terms of micrometer square, so let me rewrite this. So before that, let me write the equivalent. 11.7 times 8.9 is 104.13. 104 divided by 10, I'll write 10.413, okay, times 10 power minus 3, it becomes minus 9. So I have 10 power minus 9. Now I have micrometer in the denominator and 1 meter is there. So in order to convert that into micrometers, I will multiply here by 10 power minus 6 and below also 10 power minus 6. Then it becomes micrometer, this also becomes micrometers. So it becomes per micrometer square farad per, because epsilon naught is farad per meter, that farad is here, okay. Given this, now let's find 9 and 6 is minus 15. So we have 10.413, 10 power minus 15 is femtofarads per micrometer square. 10 power minus 15 is femto. So this is the capacitance per micrometer square. Now let's find what is the total junction capacitance from source to body. That is equal to, we have the total area is equal to area of the front side, which is 0.2 micrometers, this times this, 0.2 times 0.2. This area is covered. So 0.2 times 0.2 micrometer square. And this entire quantity is actually 2 times, because front side, okay, let me write separately, 0.2 times 0.2 micrometer square. This is front side, this is back side. And now I'll write the right side one, which is 1 micrometer times 0.2 micrometer is the area here. This is 0.2 micrometer square. This is right side, plus again left side is the same, which is 0.2 micrometer square. This is left side. So we got 4 sides, plus the bottom side, okay, the one which is facing towards the base side or the body side, body side. So which is 1 micrometer times 0.2 micrometer. So this is 0.2 micrometer square. This is on the bottom, okay. So when we add all of them, 0.2 times 0.2 is 0.04, okay. So the total area is 0.04, 0.04 is 0.08 plus 0.2, 0.2, 0.2 is 0.6. So I can write this as 0.68 micrometer square. Now the total junction capacitance, we can say source to body, is per micrometer square, that is 10.413 times 0.68. Micrometer square cancel, we get femtofarads. Let's see this value. 10.413 times 0.68. This is 7.08 femtofarad. So this is the junction capacitance. Now if you look at the options here, so option B is 7 femtofarads. That's the answer. This is the first part of the question. That's the first question. Now let's come to the second question. Here we're talking about the gate source overlap capacitance. Now if you see here, this entire thing is the gate, this entire thing. And there is source, this thing is source, okay, this is source. And we are having an overlap here, which is represented by this del, okay. And we need to find what is this gate source overlap capacitance. Now if you look at this, we have one material like this. This is, let's say, gate, and we have oxide here. Now we have another material like this, a bit more deep, okay, like this. There is an overlap here between this material gate and this source. This overlap is given by delta, which is 20 nanometers. Now let's find the capacitance between this plate and this plate. which is separated by the oxide, silicon dioxide. Okay, so let's find that capacitance will be equal to epsilon naught epsilon r of oxide divided by, now these two plates are separated by the thickness of the oxide, which is given here, the thickness of the oxide 1 nanometers. So let me write that 1 nanometers times the area. Area is nothing but the overlapping area between the gate and the source. If you see the area overlap here, this width is 1 micrometers times the overlap is del, which is 20 nanometers. So let's write this 20 nanometers. Now if we substitute the values of epsilon naught and epsilon r, 8.9 times 10 power minus 12 farad per meter times epsilon r of oxide is 3.9, and nanometers cancel, we have times 1 micrometer. Meters cancel, so micro I'll write it as 1 times 10 power minus 6. Now we have, let's multiply this, 8.9 times 3.9 is equal to 34.7, okay, times 10 power minus 18. And in fact, we forgot this 20 here. By the way, let me just put it here, 20. So 34.7 times 10 power minus 18 times 20 is there. Sorry, I missed that. So 34.7 times 20 is 694. This is 694 times 10 power minus 18 farads. We can write this as, in terms of femto, this is 0.694 femtofarads. This is 0.7 femtofarads. This gate source overlap capacitance is 0.7 femtofarads approximately. So the answer here is 0.7 femtofarads, option A.